Call section 3, day 2, vector applications, and that really means like at the end we're going to do a couple of word problems. We have a few other things to talk about before we get into the vector application. So let me find my cursor here. I'm going to start with an example, which is really like information that we have enough information from yesterday to be able to answer this very first example. And it says, find the vector v that has the given magnitude. And notice I'm saying magnitude for v should be 15. So I'm going to have a length of 15. And the same direction as u, where u goes in the direction 1, 2. So an issue that we have right here is that the vector u, named u, does not, like we could find the magnitude of the vector u, right? Square root of 1 squared plus 2 squared. It would be the square root of 5, so that's the distance of u. And then the big question would be, like, how do I get from the square root of 5 to 15? And that becomes a little bit challenging. So yesterday we made mention of something called a unit vector. And does anybody remember what's special about the unit vector? Its length or its magnitude is always 1. So if we can find a unit vector for u, then we'll have created something that goes in the same direction as u, but has a magnitude of 1. And then we could just use scalar multiplication, multiply that unit vector by 15, and now we have a magnitude of 15. So it's figuring out how you can use the small pieces of what we talked about yesterday to answer the question today. So I'm going to find the unit vector, so the magnitude is 1. And remember, for the unit vector, oops, spelled that wrong. We do that piece where we take the vector, so 1, 2, and we divide it by its magnitude. Okay, so we would divide it by the square root of 1 squared plus 2 squared. This piece right here that I have written on the board, that's from yesterday. If you look back in your yesterday's notes, we know how to find a unit vector, the vector divided by the magnitude. And that's all I'm doing. So I would come up with something like 1, 2 divided by the square root of 5. And I could write that out as 1 over the square root of 5, 2 over the square root of 5. And then rationalize my denominator. So we get square root of 5 over 5 and 2 square root of 5 over 5. So that's the vector that has magnitude of 1 that goes in the same direction as u. Now I want to create the vector v that has magnitude of 15. So I just use scalar multiplication, which is multiply that vector by 15. So here's step 1, find the unit vector, so the magnitude is 1. Here's step 2, multiply by scalar. And so we would say v is equal to 15 times my unit vector and this one works out fairly nicely. When you distribute the 15, it'll divide nicely by 5. And so our new vector should be 3 square root 5 and 3 times 2, so 6 square root 5. And this would go in the same direction as the vector 1, 2. So if I figured slope, okay, it would be the same. Y over x, 2 over 1. 6 square root 5 over 3 square root 5, also 2 over 1 when you reduce it. But this one has a magnitude of 15. So we're going to see that pop up again a little bit later. If we want a desired magnitude in a specific direction, we could use the unit vector and just multiply by the scalar. Okay, so the next slide I'm going to talk about something that is a little bit different than what we talked about yesterday. So small set of notes there. Okay, we've got, suppose you're given a problem and you're given the magnitude and the direction angle. Then we want to be able to write our vector one of two ways. Most often I'll say you'll write it in its component form. And the component form you have on the notes there is the magnitude of v times the cosine of theta. And then the vertical component is the magnitude of v times the sine of theta. So just to kind of reason through this, why this works. Suppose I have that vector v with magnitude, and I label this point, remember how we called this AB yesterday? Some point AB at the end of the vector. And I also know theta, the direction angle. If I wanted to, I could create some equations using right triangle trigonometry, using the letters A and B. Okay, which are my horizontal component A and my vertical component B. So what we know from trigonometry is the sine of theta is equal to B over the magnitude of V, opposite over hypotenuse. We also know the cosine of theta is equal to A divided by the magnitude of V, adjacent over hypotenuse. And then if I wanted to just know what A or B was, I could solve by multiplying by the magnitude, right? Okay, so multiply both sides by the magnitude. That one doesn't cancel. And they cancel over here on this side, and so we have A, the horizontal component, is the magnitude of V times the cosine of theta, which is true in our component form. And then same for B. Magnitude of V times sine theta. And then taking from that, what we talked about yesterday in terms of that linear combination, how we use the standard unit vectors, I and j, we could just write them AI plus BJ. So if we replace A and B with what we just wrote down for our component form, it would just be the magnitude of V times the cosine of theta, remember that's just A, times I, the standard unit vector in the horizontal direction, and then plus the magnitude of V times the sine of theta times J, okay, which is our vertical component. So we're going to be seeing that trig value come back into play. Now let's see how we can apply that to different problems. So my first example is if I give you a magnitude, so I'm telling you the magnitude of V is going to be 5, and I give you a direction angle, 30 degrees, can you write the component form? Well, looking back at that last slide that we just wrote down, okay, we know that component form for V looks like magnitude of V times cosine theta, and then the vertical component is magnitude of V times sine theta. So we really just have to do substitution into that component form. We know what the desired magnitude is 5. We know the direction angle is 30. So I would write something like this. V is 5 times cosine of 30, 5 times sine of 30. I do know sine and cosine for 30 degrees, correct? That'd be my pi over 6 angle on the unit circle. So we could write this as 5 times square root 3 over 2. And 5 times 1/2, I'm pulling that from my unit circle. And then I have 5 square root 3 over 2 and then 5/2 for my component form. That's all I have to do. And I did see some of you reaching for your calculators. I think we're gonna, or we could use the calculator on the next one. Okay. But if you know it from the unit circle, you could also leave it in those values and have exact answers. So why don't you try the next one? Oh, I can't get it to go. Which is, the magnitude is 2, and you want it to go in the direction of 2i plus 3j. There's two ways to answer this. You can give me exact answer, then you'd be looking sort of like at that very first problem we did. Or you can give me a more rounded answer if you calculate your direction angle. So thinking about your skills from yesterday. So I'll give you just a minute to kind of look over and decide, how are you going to attack this particular problem? If I were going to give you a hint to kind of get your brain rolling, it would be that in the linear combination, the coefficient to I is like your A, your horizontal component of your vector. Your coefficient to J is your
Connor Stanger, report to the health office, please. Connor Stanger, please report to the health office.
which is your vertical component of your vector. So if you thought about this in component form, okay, you could write that in component form as 2, 3, where that's A, that's B. So that might get some of the gears rolling from yesterday. Okay, so just really quickly so that we can kind of move on and make sure we get through all of our notes, I want to talk about two different ways that you can approach this problem. One way to approach this problem is if you know A is 2 and you know B is 3, if you look in your notes from yesterday, we know how to find direction angles. And to find direction angles, we basically set up a tangent. So we say tangent of theta is equal to B over A or 3 over 2. So then you could do the inverse tangent and say that theta is approximately, Abram, what'd you get for that?
56.3.
56.3 degrees. And then once you decide that it's 56.3 degrees, you could go back to what we did in part A, which is write that out, the magnitude times the cosine of 56.3, and the magnitude 2 times the cosine 50, or sorry, times the sine 53.3. Then you'll get a decimal answer. So we could say V equals, and we're doing 2 times cosine 56.3, or 2 times sine 56.3. And does anybody have those decimal values, what they come out to be? I don't think I have them written down. 1.1 and 1.6. Okay. The other method to solving this is to go back to that very first example that we looked at. So if you want a more exact answer, you could look at this as your vector 2, 3. You could find the unit vector for that. Oops, unit vector. Which remember, we're going to take the vector 2, 3, and we're going to divide it by its magnitude, which is 2 squared plus 3 squared. So that's 2, 3 divided by the square root of 13. Okay. And if you rationalize that, let me move my screen. Apparently I cannot. If I rationalize that, I'm going to pull this all over here. I would get something like 2 square root 13 over 13, and then 3 square root 13 all over 13. And that would be my unit vector, which I would then multiply by my magnitude 2. Okay. So V would be 2 times that vector, which would give me 4 square root 13 over 13 and 6 square root 13 over 13. Sorry, I don't know where my little extended page is gone. But if you evaluate those radicals in your calculator, same as 1.1, same as 1.6. So multiple ways to think about it. If you're going to think about the direction angle using tangent, or you're going to think about the unit vector like we did in that very first example. Okay, and that could depend on if you want an exact answer or if you're okay with a rounded answer. Okay, next up we want to find the component form for the sum of u and v given their specific direction angles. So there's a couple of things to make note of. Here you have two separate vectors, a vector u, a vector v. We want to find component form for their sum, which means we want to add them together, but before we can add them together, we actually have to find the individual component form for u and the individual component form for v. So that would be going back to that rule that we used to find component form. We have the magnitude, we have the direction angle, so I just have to plug it in. U equals 2 times cosine 45, 2 times sine 45. Since that's on my unit circle, I'm going to go ahead and do my work with exact angle values. So I'm going to say that 2 times the square root of 2 over 2 and 2 times the square root of 2 over 2. So u is really the vector square root 2 comma square root 2. And then I would repeat that process finding the component form for v. Okay, so I would do something like v equals, this time 5 times cosine 90 and 5 times sine 90. Well, that comes out to be 5 times 0 and 5 times 1. So the component form for v is 0, 5. And then this one's asking us to find the sum. So now we add them together, which we talked about yesterday, add the horizontal components, add the vertical components. So I'm going to say u plus v is square root 2 plus 0, comma square root 2 plus 5. And I could simplify that to be just square root 2, comma square root 2 plus 5. And I have the sum. So multiple steps there, but if you know that rule for writing in component form, given a vector's magnitude and its direction angle, it's actually quite easy. Okay, just plug that in. Now the last two examples that we have to talk about are those sort of more application problems in that we have to read it, we'll have to decide what does the picture look like, what is the question asking me to find, and what part of all the things of vectors that we've talked about am I going to use to get my answer. Okay. So we'll go ahead and we'll start with the first example, which is a gun with a muzzle velocity of 1,200 feet per second is fired at an angle 6 degrees above the horizontal. Find the vertical and horizontal components of the velocity. So we really want to get it in component form so that we could identify the vertical and the horizontal component of the velocity. I'm going to start by drawing myself a picture. There's a person. The gun would be in their hand. Horizontal would be straight out from there. And we're firing at 6 degrees above the horizontal. So I'm going to make my angle right there as 6 degrees. So when I think about what we know about vectors, that to me is my now direction angle, coming from the positive x-axis and going up. So I have a 6 degree. And my velocity is 1,200 feet per second. So that would be like my magnitude over here, where the bullet would actually be going. so 1,200 feet per second. And what I'm curious about finding are the vertical and the horizontal components. So I'd like to know what's the vertical and the horizontal component of that velocity. And so it's really like I'm looking again for like that A and B of my vector. So I'm just going to use my component form for V. I'm going to write the vector. And it would be my magnitude, 1,200 feet per second, times cosine of my direction angle. And then my magnitude times sine of my direction angle. And there I have horizontal and vertical component listed out in vector component form. Go to my calculator and get an estimate here. So I would type those in. I came up, oh, I didn't have this one written down because I changed it. Can somebody tell me what you get for your horizontal component? $1,193.4. Can someone second that for me? Evie says yes. And what about my vertical component? 125.4. So in terms of this problem, remember we do have a label in the problem. If I were going to list out my answer, I would say that my horizontal component is that number 1,193.4 feet per second. That's the horizontal component of my velocity. And then the vertical component of my velocity would be 125.4 feet per second. So if I understand that that question is just asking about horizontal and vertical components, which I can easily spot in component form, then I realize like that isn't a really super hard question. It's just kind of figuring out what it is that is asking. We have one other problem that we want to look at. Okay, and this is one where we have multiple things happening at the same time. Okay. So this example says, forces with magnitudes of 2,000 newtons and 900 newtons act on a machine part at angles of 30 and negative 45 degrees respectively with the x-axis. Find the direction and the magnitude of the resultant of these forces. Okay, so there's really like two parts to this problem when I read it. The first part is that very first sentence is going to tell me how to set up my picture. And my picture will help me to answer my problem. Okay, so I'm going to draw a picture to begin with. The second part of this problem is that it gives you the direction of what it wants. It wants a direction and a magnitude, so I've got to have two parts to my answer. And it's of the resultant of the forces. What did we say about the resultant yesterday? What does that mean? The resultant is the answer to a vector addition problem. So it's a lot like that problem where we want to find the two separate components, then we'll want to add them together. After we add them together to get the resultant, then we're going to find direction and magnitude. So we've got multiple steps that are going to be at play here. Okay. So I've got forces with different magnitudes acting on a machine part in respect to the x-axis. So I'm going to go ahead and put my x-axis right here. Okay. And I've got different direction angles. One is a positive 30, and one is a negative 45. And then my forces, my magnitudes would be listed there as 2,000 newtons and 900 newtons. So we want to get the resultant of these two vectors, it'd be nice to have the vectors in component form. So I think we have enough information to get our two components. I'll go ahead and label this one U and this one V, and then I'll just kind of do my work from there. So to find the component form for U, I would do 2,000 times cosine 30 and 2,000 times sine 30. Oops. It's the hardest part of vectors for me is drawing the right bracket. And I know the cosine of 30, you could get decimals here if you wanted to, but just to kind of work a little quicker, the cosine of 30 is square root of 3 over 2, so that would be 1,000 times the square root of 3. And then this one will be 2,000 times 1/2, which is 1,000. Okay, so that works out pretty nicely for me. If you wrote it as a decimal, that would be fine with me. Then I'm going to find the vector component form for V. So I'm going to do 900 times cosine of negative 45 and 900 times sine of negative 45. And again, those are on the unit circle, so I can do them. It would be square root 2 over 2 and negative square root 2 over 2. So I'm going to come up with something for V like, let's see, 900 divided by 2 is 450 square root 2. And then this one will be negative square root 2 over 2, so negative 450 square root 2. Which you could get as a decimal. Okay, and would be fine. And now we want to find the resultant. So the resultant would mean add those together. So I'm going to do U plus V. And I would probably at this point just sort of transfer into decimal form. Okay, that would be most easy for us to work with. So I get the resultant vector to be 2,368.45 and 363.60. I'm going to type those in. Am I okay with that, or do you see a problem?
No, I'm just using the decimal.
Oh, you're using the decimal from the beginning. So we might be off by slight numbers. Okay, yeah, something small. Now, is that the answer that I want? Brad says no. If you go back and you read that second thing, it doesn't want just the resultant. It wants the magnitude and the direction angle of the resultant. So for magnitude, we have that formula where we can, in component form, we can just do the square root of 2,368.45 squared plus 363.60 squared. And when I do that, I got 2,396.2 newtons.
Please rise and join me in the pledge of allegiance. To the flag of the United States.
That to find direction angles, if we have component form, this is like our A and our B. And so for the direction angle, we would write the tangent of theta is equal to 363.6 divided by 2,368.45, and then we would arctangent both sides. And I think I get something like 8.7. It's a small angle. Yeah, 8.73 is what I get when I type that in. Okay, so my direction angle for my resultant is an 8.73 degree angle. So again, kind of making sense of all the little parts about vectors that we've talked about so far.